last few lectures I have discussed to you about the paralytic transformation in iron carbon system. As you know, there are 3 different transformations which needs to be discussed as a part of the iron carbon phase diagram. First one is the diffusion control paralytic transformations, in which gamma transform to perlite below 723 degree Celsius temperature, or what is known as A1 temperature, as well as when you quench a steel from high temperature, gamma can transform to martensite by diffusionless transformations, and third one is the transformation of gamma to bainite. So, in today's lecture I am going to finish off the portions which I could not do in the last lecture, that is the transformations of for the hypereutectoid steels, and then I will finally discuss a little bit of about paralytic transformation rate, how the transformation actually happens, and in the if the time permits I will move into the martensites, otherwise I will discuss martensite in the next class. So, as you know, austenite to paralytic transformations is basically a diffusion control transformation, in which the single phase FCC austenite undergoes a transformation leading to the formation of alpha ferrite and cementite in a lamellar morphology, and that is what is known as perlite. This transformation is predominantly controlled by diffusion of carbon, and it happens temperatures below A1, specifically for plain carbon 0.8% carbon steel. This happens at a temperature of 727 degree Celsius temperature. So, I discussed with you about these transformations in which perlite forms and how the transformation actually happens, and followed by I discussed with you about the transformation in hypoeutectoid steels, that means steels whose carbon concentration is less than 0.8, and I was supposed to discuss the hypereutectoid steels, that is steels which concentrates more than 0.8. So, in the for the hypoeutectoid steels, the phase which forms from the gamma is from the gamma first is the alpha. That is what is shown in this picture. I am going to discuss it from this phase diagram, because that is my base. So, as you see here, this is the hypoeutectoid steel composition, what I write hypo. So, any steel which has a composition or carbon concentration less than 0.8 is known as hypoeutectoid steel. So, therefore, if I take a steel composition like this and start cooling from gamma region, which is about 950 degree Celsius temperature, suppose here, because this is 910. So, if I cooling down from the 950 degree Celsius temperature, first phase which will form gamma is a alpha, and alpha you know is a very low carbon containing phase, is almost a very low or 0 carbon concentration at room temperature. And finally, if you cool down below 727 or A1 temperature, this will remaining gamma will transform to perlite. Alpha, which forms first from the liquid from the gamma, can have different morphologies. I discussed with you most important morphology is the gain boundary allotriomorph, and it looks like gain like this leg shaped particle which is forming between 2 gamma grains. This is known as gain boundary allotriomorph, and it can also be having the plate shaped morphology known as Woodman-Stratton pattern morphology. So, when the alpha actually, the reason alpha predominantly form in the gain boundaries, because gain boundaries are the regions where carbon diffusion can happen very easily. So, as you know, alpha contains very low amount of carbon, but austenite contains quite large amount of carbon. So, carbon needs to be diffused out when the alpha grows. So, that diffusion process of carbon can be very fast if alpha forms along the gain boundaries, because gain boundaries are the sinks of carbon or the paths of fast diffusion, normally it is the gain boundaries. So, as soon as the alpha forms, it rejects carbon in the nearby gamma region, nearby gamma grains, and therefore, the growth of alpha is predominantly dependent upon how fast it can reject the gamma, and because of that alpha grows initially lengthwise direction in the along the gain boundary. Initially it grows these 2 arrows directions as I showed you in this picture, and when it becomes very long, and or if the another alpha which is going here, the diffusion field of this alpha and this alpha they merge, then only they start elongating on the inside the grains of gamma, correct. That is what will happen. Initially they will elongate along the gain boundaries because of the fast diffusion, and when the diffusion paths of these two neighboring alpha will intersect or will have no carbon available, whatever the situation, then they will try to move into the two gamma grains. That is why the alpha forms this along the gain boundaries. And it can also be like a Widman-Staton morphology plates, which I have discussed, okay, like this. So, these are Widman-Staton plates, Widman-Staton plates. They can grow inside the grain of gamma very easily it can grow into the gamma, and predominantly this morphology is observed in the steel samples for the hypereutectoid steel. So, that is about the alpha, and once the alpha forms and alpha will reject carbon, so therefore remaining gamma will be enriched in carbon, and once this gamma will be having a carbon concentration of 0.8 and the temperature will reach below A1, the gamma will transform to perlite. So, that is how the whole transformation of the hypereutectoid steel will happen. So, now let us consider what will happen for a hypereutectoid steel. For the hypereutectoid steel, I have marked a steel composition of 1 atom weight percent of carbon. So, any steel composition beyond 0.8 for plain carbon steel is known as hypereutectoid steel. Okay, any steel, it can be 0.9, 1. I am just taking one example, which is 1% carbon. So, what is going to happen here? Again, if I take the steel sample at about 950 degrees Celsius temperature, suppose somewhere here, it will have a single phase gamma microstructure. That means all the grains will be gamma. So, at this temperature, all the grains will be gamma, large grains of gamma, as you see here, these are the gamma grains. Nothing will happen below this, above this temperature, which is this temperature at which this is called ACM line, that is the line or curve which demarcates the phase stability between gamma and the cementite. That is why it is called ACM, CM stands for cementite. So, below ACM, cementite will form. This cementite is again primary cementite, like alpha, primary alpha which forms here. So, again this cementite, so if I say this is T equal to 950 degrees Celsius temperature, and if I draw the same picture T below ACM, what will happen? Its gamma grains will remain, and this gamma grains will remain, whereas the cementite will nucleate along the gamma grains boundaries, because gain boundaries are the regions in which diffusion of carbon happens fast. As you know, if the alloy composition is 1% carbon, that means each of these gamma grain will have 1% carbon. On the other hand, cementite contains 6.67 weight% of carbon. So, from 1 to 6.67% carbon is difference is very large. So, therefore, if you want to form this cementite containing about 6.6 weight% carbon, you need carbon diffusing from gamma grains to these places. Carbon should diffuse and reach these places for cementite to grow. So, if the carbon normally diffuses very fast in the gain boundaries, any pieces will diffuse very fast in the gain boundaries, that is because gain boundaries are regions of defective. There are a lot of defects on the gain boundaries. When the two grains meets, there will be many vacant sites, there will be dislocations. In fact, small gain boundary is nothing but a row of dislocations. So, these are the reasons why diffusion of carbon can happen very fast along the gain boundaries, and that is why the cementite nucleates on the prior gamma gain boundaries, and then the cementite lamellae will grow along the gain boundaries. That means again they will lengthen along the gamma gain boundaries. This is cementite because of the faster diffusion path. Finally, this lengthening will stop when another cementite lamellae will intersect or meet the central cementite lamellae. Okay. So, this one was growing along the length of the gamma gain boundary. This lengthening along the gain boundary will stop when this top one or the bottom one will meet the boundaries here. That is what will happen. In for the again, if you allow more time or more diffusion to happen, the cementite lamellae, these cementite grains will then again grow into the gamma grain inside it. But normally we do not see it happening. Why? That is because amount of primary cementite will form is very low percentage. Why? That can be calculated. So, let us do that calculation using the lever rule. So, my alloy composition is 1% carbon, right. So, my Falcam will be at 1% carbon, and this is 0.8 where the perlite forms, and cementite composition is 6.67. So, this is cementite, right. So, this is gamma. So, I am calculating the percentage of cementite above A1 temperature, that cementite is the primary cementite which will form along the gain boundaries. So, what is the percentage of cementite? Very easy, you can do yourself. This is this, so this is 0.8, this is this arm divided by total arm. What is that? So, 1 minus 0.8 divided by, so I am taking this arm divided by the whole arm, 6.67 minus 0.8 into 100. So, this is 0.2 divided by, so this much is 7, so 8, 5.87 into 100. So, it will come like about 11%, very small, very small, okay. So, not even below 11%, 20, yeah, 20 divided by 5.87, this will come about 4%, that is all, very low. So, as you see here, if the total volume percentage of this primary cementite is 4%, so that means these phases will be lying along the gain boundaries only. They will not become fatter, or they will not grow along the inside these gamma grains, because that much of cementite will not form in the microstructure. So, by simple using lever rule, you can clearly show that cementite volume fraction will be much lower. On the other hand, I have also done the calculation for the primary alpha, which will form if you cool down from this temperature to this A1 temperature, that will be very large, that can be 25% or even 30% or 50%, not 4%. So, because the total volume fraction of the primary cementite forming at 1% of 100% of the carbon concentration alloy is only 4%, so they will only lying on the gain boundaries. So, that is what will happen below ACM temperature. Now, at temperature, so therefore, as the cementite forms, what will happen? This is, if you look at it, although gamma grains all are having 1% carbon concentration, cementite having larger amount of carbon concentration will take away the carbon from the gamma grains, that I have shown by arrows. The carbon will diffuse from the cementite, from the gamma grains into cementites, you see here, that is what will happen. So, because of the diffusion of carbon, these gamma grains will be having less and less amount of carbon, will become lean in carbon concentration, or rather I can say the gamma carbon concentration gamma will follow this line, ACM line, as you lower the temperature. As you lower the temperature slowly, the carbon concentration gamma grain will drop, a drop along this line, which can be followed by this line ACM on the phase diagram. So, finally, at a temperature below A1, whatever gamma grains will remain, those gamma grains will transform to perlite, right. So, these are all the cementite, these are all cementite which have grown along these boundaries, it is very small, okay. So, and these grains will then transform into perlite. So, that is what is the microstructure you will get for the hypereutectoid steel. So, this is alpha, this is Fe3C. This is also Fe3C, but we call this as a primary or pro-eutectoid. So, this Fe3C is primary or pro-eutectoid cementite. Why it is called pro-eutectoid? That is because it is formed before the eutectoid reaction. Eutectoid reaction happens in below A1 temperatures. So, anything forming above a temperature above this eutectoid transformation temperature is called pro-eutectoid. So, that is why it is called pro-eutectoid cementite, and this cementite which is inside in the perlite lamellae is known as paralytic cementite, okay, or because it forms due to paralytic transformations. So, you must know difference between these. This has formed by different mechanism than this one. So, these cementite which are marked as a primary, they form by nucleation and growth on the grain boundaries of gamma from the at a temperature above A1, but these forms by eutectoid transformations, again obviously nucleation and growth is involved, but eutectoid transformation which is cooperative type from the gamma to form both cementite and alpha. So, that is exactly how the cementites lamellae will form. Now, I have given you the whole picture. Let me just show you some microstructures. Okay. So, yeah. So, here I am showing you 3 microstructures which I have shown you earlier. This is the perlite, as you see here. This is for the eutectoid steel, perlite, for the eutectoid composition, that is 0.8. The left, this picture is for the hypoeutectoid steel, where you can see large amount of the primary alpha and the perlite. Perlite is very easily discernible from the microstructure. On the right side you have hypereutectoid steel, in which primary cementite has formed as along the grain boundaries, very small volume percentage. You see here only along the grain boundaries it has formed, and within the grains or prior gamma grains, what you have is a perlite, typical lamellar microstructure. That is what you see in these grains, correct. So, that the major difference between hypoeutectoid steel and hypereutectoid steel is there. In hypereutectoid steel you will see large big alpha grains, primary alpha grains. On the hypereutectoid steel you will see small amount of the cementite, primary cementite forming along the grain boundaries of gamma. These alpha also started forming on the grain boundaries of gamma, but they have grown, and because their volume percentage according to the phase diagram calculation is very large. So, that is what you see large gain of the gamma. So, this you must keep in mind, because this is very important. Remember, majority of the steels in this world are actually hypoeutectoid steels, 0.3, 0.4, 0.5% of the carbon, or even less, 0.1, but very small amount of the steels which use are hypereutectoid steels. Because in hypereutectoid steels you have a primary cementite present, these steels are very brittle but very strong. All our knives, cutlery, even blades, they are made of hypereutectoid steel. Shaving blades which are having very thin edge are made of hypereutectoid steels. Okay. So, that is the important thing about the hypereutectoid steel. Hypereutectoid steels are not used in large quantities, but they are used for specific applications, and these applications demand high strength. Okay. Ductility may be poor, but high strength. If you want to create a knife, edge should be very sharp. To keep a sharp edge on the knife, you need a strong material, hard material, so that it should not bend, it should not get deformed when you are cutting something. So, that is why actually this microstructure becomes very important. So, the properties of the steels actually completely depend on the microstructure you develop, and microstructure depends on the phase diagram, also processing conditions, but here it is completely dependent on the phase diagrams. So, I told you that how actually the hypereutectoid steel transformations happens. Now, another 5-6 minutes what I have, I just want to discuss with you the way the paralytic transformations rate changes. As you know, paralytic transformations, which what is happening inside these grains, it depends on the carbon concentrations in the steel. It depends on the carbon concentration in the carbon diffusion in the steel, or diffusion of carbon in the along the gamma in the transformations. So, perlite, which actually happens for 0.8 carbon percentage steel, if I take a 0.8 carbon percentage steel and temperature above T1, above A1, they will have all gamma grains, and as soon as you cool below T1, below A1 temperature, these gamma grains will transform will transform into perlite, and this is the way we show this perlite lamellar morphology. And I show the orientation of this lamella differently in different grains, just to make sure that they are forming in different ways. So my question is this: when these transform to perlite gamma, what is the rate at which transformation happens? Normally the rate of transformation depends on two things. One is the kinetic factor, second one is the thermodynamic factor. What is the kinetic factor? Kinetic factor is the diffusion of carbon. Why? Why you need to diffusion of carbon? See, remember, these gamma grains contains all 0.8% carbon. Now from this I am forming two phases. One is cementite, which is carbon rich, other one is alpha, which is carbon lean. Alpha do not contain any carbon at room temperature. High temperature it contains about 0.02% of carbon. So therefore, but on the other hand, cementite contains 6.67% carbon. So this large difference of the carbon concentration in gamma and cementite is only possible when there is a diffusion. Okay. So whole transformations from single phase gamma to two phase cementite plus alpha is basically dominated by carbon diffusion. And as you know, diffusion is low at lower temperatures. So if you cool the sample, undercool the sample, suppose much low the A1 temperature, diffusion will be very, very low. So when the diffusion is low, the thickness of this lamellae will also be low. That is obvious, because the carbon cannot diffuse longer distances. So if carbon cannot diffuse longer distances, thickness of this lamellae will be smaller, or in the other hand, the distance between the two lamellae will be smaller. That is what is the interlamellar spacing, we know lambda. So lambda will be small when the diffusion is temperature is low. If the temperature is low, lambda will be small, because diffusivity depends on temperature. How? d0 into exponential minus q by RT, where d0 is a p exponential constant and q is a basically activation barrier height and T is the temperature. So as you increase the temperature, D will be high, as you decrease the temperature, D will be low. So therefore when T is low, diffusion is low. If diffusion is low, the thickness of these lamellae are also low, and therefore lambda is small. So this is the effect of kinetics, that is the effect of diffusion. Now as you know, as you undercool the things lower, that means when the temperature is lower, the diving force is diving force will be high. Why? Because diving force depends on the undercooling. As you increase the undercooling, diving force will increase. The diving force is what? Diving force is nothing but delta G. That is G of product phase, that is here you perlite, minus G of gamma. That is the diving force. So this diving force is summation of diving force of cementite and the alpha. But so if the temperature is low, this is high. If this is high, that means the rate of transformation is also very high. Correct? That is what is the opposite factor. So as you know, temperature is lower means diffusion is low, but temperature lower means diving force is high. On the other hand, if the temperature is high, diffusion will be higher, but diving force will be lower. So these two factors actually act in a very different way, in opposite direction. So that is why if you want to really plot the rate of transformation as a function of temperature, okay, suppose this is my temperature and this is the transformation rate R, so this will be like this. Why? As you are at the higher temperature, this is suppose somewhat A1 temperature, obviously very close to A1 temperature there will be no transformation happening. Why? Because there is no diving force available, and if the temperature is very low, there will be no transformation happening because diffusion cannot happen. So transformation can only happen if temperature range from these to these, at up to which in which the transformation, as you decrease the temperature from this to this, transformation will keep on increasing. Okay, it will increase very fast. Why? Because this is the temperature domain in which both diffusion is also good and diving force is available. On the other hand, if you reduce the temperature further below, diving force may be high, but diffusion is slow. So therefore the transformation rate will decrease. So this is like an inverse C curve. You understand that the inverse C curve? Origin of the inverse C curve is because of these opposing two factors. One is the temperature, other one is the diving force. So, diffusion is lower as you decrease the temperature, but driving force is higher. And so, therefore, this higher driving force at lower temperature is basically used to create more of these interfaces. As you decrease the lambda, more number of interfaces will be created. So, more number of interfaces can be only balanced, energy can be balanced by providing more driving force. So, at higher temperatures, which is close to this temperature, the paralytic lamellae will be very, the lamellae means lambda will be very large. On the other hand, lower temperature lambda will be low, but your the reason is diffusion, main reason is diffusion. So, you please keep your understanding that this curve, transformation curve of parallite as a function of R is the rate. So, you can say centimeter per second or micron per second, okay, and this is a temperature, this looks like inverse C curve. So, if I plot it in other way, that is if I plot it time versus temperature, it will be like looking like this kind, it will be the opposite to that, because here this is rate. So, you inverse it, take the time up, so it will be opposite. That we will come back to it when we discuss about TTT diagrams. So, with this I have given a very small introduction of this rate, because this is a part of the phase transformation of material. So, I do not have time, or I cannot go in detail of this of the transformation, but I have told you the subtle features, that how the transformation, paralytic transformation will happen, or the rate it depends on. Now, question is that if I take a hypereutectoid steel or hypereutectoid steel, the transformation rate will also be depending on how this primary alpha or proeutectoid alpha or proeutectoid cementite will form. So, that means if I want to really discuss about the hypo and hypereutectoid steel transformation rates, I should also be talking about two different transformation rate, one at a temperature above A1, one at a temperature below A1. So, below 1 this will follow this, because below 1 only paralytic transformation happen, above A1 transformation rate of alpha or cementite which is forming above the A1 temperature will be different definitely. So, that if time permits I will discuss. So, I have given you a brief good idea about how hypereutectoid and hypereutectoid steel microstructure develop as a function of temperature, and I have also told you what is the way paralytic transformation rate depends on, what are the factors which it controls. So, normally lambda, just to give you a mathematical formula, lambda, let me see, I have written somewhere, yeah, lambda actually depends on these factors, okay, let me just write it down, because this formula is also very important. Lambda actually depends on following factors. What are the factors? It is written as like this, 6 gamma Vmt divided by delta H m into delta T. So, 6 is numerical C, gamma is the interfacial energy between alpha and cementite, Pm is the molar volume, volume per density, and of the unit mole, mass T is the eutectoid temperature, that is the A1 temperature, delta H is the heat of evolution during transformations, and delta T is the most important factor, that is the undercooling, that is the temperature below which you have to cool, below A1 you have to cool to start the transformation, that is what is the delta T. So, as you see here, as the delta T increases, lambda will decrease, okay, that is very clear. As you decrease the temperature, lambda will decrease, as you increase temperature, lambda will increase, and delta T is nothing but Te minus T, okay, T is the eutectoid temperature. So, that is all for the paralytic transformations. In the next class we are going to discuss about martensites, start discussing martensites.